Okay, thank you, everyone. Thank you, Claudia, for the invitation. The idea here is to present what is the status of the new MPI ABI initiative within MPI for Python, what is the main problem that I'm looking the ABI to solve, and in general, what is the current status of the initiative. I will start with a very brief introduction about what is MPI for Python, which is known in short as MPI for Py. MPI for Python is an unofficial Python binding for MPI, unofficial simply because it's not standardized by the MPI standard, but it's only a beast of my own breed. The API of MPI for Python is based on the MPI2 C++ bindings, sorry. That didn't age very well because nowadays the bindings are deprecated, but other than that, the resemblance is remarkable, I would say. And the original intention was to make things easy to learn for users, because once you knew C++ and the C++ bindings, translating things to Python was really straightforward. Nowadays, with only C and Fortran surviving as the official language bindings, that connection is a little bit of, it's not that strong, but anyway. One remarkable feature or detail is that MPI for Python supports almost all of MPI. MPI for Python is best suited for an MPI 4 implementation, but it also works with MPI 1, 2, or 3 implementations. Of course, if you try to use a feature that is not in the MPI library that you are using as a backend, you will get an error at runtime. What are the features? Well, this is an enumeration. It's maybe a little bit redundant, all these slides for the audience. Everything from MPI 1, point-to-point communication, collectives, groups, communicators, virtual topologies. And then MPI 2, with added quite a bit of additional stuff to MPI 1, parallel I/O, dynamic process management, one-sided operations, or RMA. Finally, the features from, no, not finally, MPI 3 added matching probes, non-blocking collectives, neighbor collectives. And finally, MPI 4, which is relatively recent, added some additional features, persistent collectives, partition communication sessions, and the large count API. After, as Chef said, 20 years, finally, we got that. And right now, the latest version of MPI for Py uses the large count API exclusively. This way, I will never, ever again will have the complaints from users trying to send large messages and not being able to do so and coming back to me asking about what to do. As a summary, the current MPI API is relatively large. We have, in total, up to today, 960 symbols and constants overall. Here you have basically an accounting of how much each major version of the standard was adding. MPI 4 added 160 something additional routines to support the large count versions of the routines. And again, all of that is supported in MPI for Py. MPI for Py makes use of all those routines. And in some sense, because it's a special piece of software in the sense that it's a language binding, MPI for Py is kind of the ideal project or the ideal code to test all of this ABI stuff, simply because MPI for Py covers everything, okay? And it's relatively easy to catch any oversights or mistakes. And that was kind of the role of MPI for Py, of using MPI for Py as a testing tool for the MPI ABI. This is a small example of how MPI for Py is used. The classical hello world, you import the MPI module from MPI for Py, from the MPI for Py namespace or package. Then you access objects, which typically are the handles, and you call methods from those objects. And well, you do your usual parallel programming. the typical way to run is to execute Python with whatever process launcher or executor you have. If you're in a laptop or desktop, probably you will use MPI exec or MPI run. If you're in a batch system, you will use srun, prun, whatever. You execute Python and Python runs a script. How people use MPI for Pi, or how they actually get it installed in their computers or laptop. If they are going to do it by themselves from sources, what they basically do is execute pip install MPI for Pi. When you execute that command, basically pip, the Python package manager, will download the MPI for Pi sources, which are written in Cython. The Cython code is a mixture of C and Python. And Cython, what does is to translate that extended Python language, let's say, to some gigantic monolithic C file that currently weighs about 13 megabytes with a lot of cryptic and mangled C code. All of that is fed into the C compiler and the linker. The C compiler, of course, uses the Python header files, the MPI header files, and at the link step, the MPI share library. And with that, the final result is an extension module, which is no more than a special share library that Python opens at runtime to access all the functionality in the module. So that's basically the procedure to get MPI for Pi up and running. The problem with this approach is that it's time consuming. The users have to download the tarball. They have to download. Everything is automatic, but still it adds time to the process of getting MPI for Pi ready. You need to download and install Cython in some Scratch environment to do the compilation. You need to generate this gigantic C file. Then you have to invoke the C compiler to finally get the extension module to run on your platform. If you are doing this inside containers, for instance, this will force you to download a lot of packages to do the compilation process. You need development headers, libraries, the compiler itself, and all that adds weight and time to the process, not to mention that sometimes users which are not savvy with compilation in general struggle to get things done. They have semi-broken development environments, and that is always a hassle for people. So how this is alleviated? Well, by using pre-built MPI for Pi binaries. Third parties already provide MPI for Pi binaries. By third party, I mean people who are completely outside of the MPI for Pi project. They are just downstream distributors. For instance, in macOS, Homebrew uses OpenMPI as default, and then MPI for Pi works with that default OpenMPI package. And in MacPort, they took the other choice. They use MPitch, and MPI for Pi in MacPort use MPI for Pi. So MPI for Pi uses MPitch. You have no options. If you want to swap or switch the MPI implementation, you need to compile MPI for Pi from sources with a previous procedure. In Linux distributions, well, things vary depending on implementation. In the case of MPitch or OpenMPI, or both can be supported, sometimes using modules, and some other time using alternatives. But in general, in most of cases, you have to repeat or recompile or rebuild all the packages for one or the other or both. An important, at least for me, case is CondaForge, in which I am involved, where with the Conda package manager, you can create virtual environments to execute a plethora of different libraries, not exclusively Python, but also other languages. And in the particular case of MPI for Pi, but this is not exclusive to MPI for Pi, it also applies to any other MPI library, we basically have to compile or build everything for all the different supported MPI implementations in CondaForge. And that amounts to supporting MPIC and OpenMPI on POSIX platforms, that is Linux and macOS. Also, in the case of Linux, we support Intel MPI, also on Windows, and exclusively to Windows, Microsoft MPI. So from this configuration file where we have all the different combinations of MPIs that we will use in each platform, we end up with 65 builds. Of course, many of those builds correspond to different Python versions. So the problem is not exclusive to MPI. I mean, the explosion of builds is not only fault of MPI. The fact is that we support different Python versions. That's fine. But for sure, we have a factor of 2 or 3 of additional packages just because of the need of building for different MPIs. Okay. Another solution, and one in which I am particularly involved, is the production or the distribution of Python wheels. What are Python wheels? Well, they are just zip files which are ready to install with a bunch of files that you basically unpack in some directory, and you can start using the package. So, in order to try to support a single package that can operate with multiple MPI implementations in a variety of environments, from a supercomputer to a desktop or laptop, what I am doing is creating a specialized packaging where I produce for the different platforms and the different architectures a package that contains many individual compilations of the main MPI module, which are tagged in the file name, as you can see here in the lower right, by the MPI major and minor version and the MPI implementation. So the idea here is that by intercepting the usual, or by hooking in the usual or the default Python import mechanism, what I do is I preload the MPI library at runtime. I look for MPIC or OpenMPI. The first that I find, I use it as the default, or as I assume that is the default MPI the user wants to use. By querying on the MPI library, I'm able to dispatch at runtime and pick the particular version of the module that will actually service the user. All of this, of course, is non-standard. It's built on top of standard Python APIs, but it is unusual to implement this kind of machineries. This is kind of okay for many users because you basically get something that is able to run whatever MPI you have. You can switch from one to the other just maybe by changing your path and your LD library path. The minor problem of this approach is that the wheel file that you have to download has a lot of different builds that maybe you will not use or will not need, and that is some extra weight in the package that maybe you would like to avoid. All those Python wheels are distributed in anaconda.org. To install them, you need to add some special options to the pip package manager. You have to tell explicitly that you want to install MPI for Pi not from the usual default location, which is the Python package index, but from this special site, from this special package index, which is hosted by anaconda.org. Is this useful? Does anyone care? Does the community need all this special packaging? Well, as you can see here, over the last year, all this is relatively new. It started in 2024. We are already accumulating some downloads, so people are using this. People are using these packages. Given or taking into account that you explicitly have to request the installation from some specific place using non-standard command line arguments, I would say that there is interest on using these packages to perform quick deployment of MPI4Pi. So I would say that if this approach ever becomes mainstream, the user community would probably appreciate all this effort. Regarding the ABI comes, or my intention or my expectation is that the ABI will simplify all this duplication of binaries and compilations, because the idea is compile once, run everywhere with different MPI implementations. And that is already kind of supported and implemented in MPI4Pi. We have it working in continuous integration in GitHub Actions. And what we do is basically a two-step process to test all this infrastructure. In a build step, we use the MPI stubs. The MPI stubs, you have here the URL, is just a dummy library with a header file and a shared library that contains all the MPI symbols according to the ABI specification, to the current ABI specification. And of course, if you try to use that library at runtime, basically your code aborts, because the idea is that this library is used only for compilation. And in the build step, we basically build MPI4Pi as usual, and we generate a Python wheel file the usual way. There was no requirement to change MPI4Pi source code basically to do this. The purpose of the ABI is to be completely backward, or the intention is to be completely backward compatible, and somehow MPI4Pi proved the point that was something that we could achieve. And then after that, in a test step, I basically clone the mpich repository. I configure the repository with a special flag to enable the ABI library. And after that, I install the Python wheel from the previous step, and I run all the test suite of MPI4Pi. And well, I would say that overall the whole task at the end was successful. We can build Python wheels that use the ABI, and they are compiled without a true MPI library. Later on, we can use that binary and run it as usual with a concrete MPI implementation. For now, only mpich, and everything works as expected. Where do I want to end with all this mess of binary distribution? Well, for once, to use the MPI, once we standardize the MPI ABI, using probably weak symbols, which is something that someday I'll have to discuss with Jeff, whether we could mention something about this in the standard. I'm not sure, because it's a platform-specific thing. But by using the ABI with support for weak symbols, we could use or compile for multiple, we could run with multiple MPI standard versions in the library and detect at runtime whether a function is available or not. On top of that, we could use the Python's own ABI, which is called limited API, to build a single module that could run with multiple Python versions. With those two ingredients, we could really generate one Python wheel per each operating system and architecture that basically would resume or would produce a single package with only one extension module, as shown in the right, that would replace multiple different packages or builds, which in turn internally have multiple different variants of the module compiled for different MPI standards and MPI implementations. Finally, a comment about the time machine. If I could go back in time and I had the MPI ABI 10 years, 15 years ago, maybe the approach to implementing MPI for Pi could have been completely different. And that would allow me to get rid of dealing with C compilers and pre-built binaries. What I would do instead is to dynamically load the MPI library at runtime, and then call MPI routines using C types, which is a built-in module in Python to interoperate with shared libraries, or with CFFI, which is a much nicer package, in my personal opinion, that does basically the same, that allows you to access functions from shared libraries at runtime, call them, and use C libraries with no problem from Python. The nicety of this approach is that basically you have pure Python code working with any MPI ABI implementation. There is no need to compile, no need to rely on C compilers, no need to deal with broken environments in the user's side. The only drawback is that it might be slightly slower in hotspots, but this is just the usual Python calling overhead. So, I mean, every Python user at this point kind of lives with that. Okay, well, finally, many thanks for your attention. Just a few links here, the MPI for Pi repository at GitHub. The second link is the place where I host these pre-built binaries. And finally, a GitHub repository where we discuss and people submit issues with the ABI. And finally, last link, a pointer to our current version of the header and stubs library. That is something that you can use with your own code to check how ready or what possible troubles you could have compiling your own code with the new MPI ABI. It's a good thing if anyone is interested to try it out and report back if there is any particular issue. And that's all. Thank you.